The question is like this: using the properties of determinant, prove that the determinant is equal to 4 times a square, b square, c square. Okay, so in this question we have to use the property of determinant, right? So one thing more which can be a point of confusion is this, that we have to prove this determinant equal to a certain value. Okay, this cannot be done without expansion. Okay, so to solve this question, okay, we have to use the properties of determinant, right? But at any stage of the question, we feel like the determinant has converted into easy form, we will also have to expand the determinant. Whenever a determinant is given equal to a certain value, it cannot be proven to that given value without expanding the determinant, right? So to solve this question, first of all, taking left hand side, I've been given determinant a square ab ac, ba minus b square bc, ca cb minus c square. So the thing you see here in this determinant is this, that is, on analyzing the terms of this question, we can easily take a common from the first row, b common from the second row, and c common from the third row, right? So taking a common from r1, b common from r2, and c common from r3, I'm going to get this as abc. From a square, I'm going to get on taking a common as equal to a. From ab, if I take a common, I'm going to get b. From ac, if I take a common, I'm going to get c. From ba, if I'm going to take b common, I'm going to get a. From minus b square, I'm going to get minus b, and so on. Okay, so this is how I've taken a, b, c common from the determinant, right? Again, I see here that from the column 1, column 2, column 3, I can again take a, b, and c as common. Okay, so taking a common from c1, b common from c2, c common from c3, I'm going to get a square, b square, c square is equal to minus 1, 1, 1, 1 minus 1, 1, 1, 1 minus 1, right? So taking the determinant and applying the property, R2 is changed to R2 plus R1 and R3 is changed to R3 plus R1. This property is applied because if I add the elements of the first row to the element of the second row, I'm going to get 1 minus 1, 0 here. And similarly, if I add the element of the first row to the element of the third row, I get 1 minus 1 again as equal to 0. So I get 2 zeros in the first column. Okay, and whenever we have to make an expansion of the determinant easier, we make maximum number of zeros in that determinant, and if a column has 2 zeros, then the determinant solvation is very easy. Okay, so applying the properties, I'm going to get this as a square, b square, c square into the first row as it is. The second row will be 1 plus minus 1, minus 1 plus 1, and 1 plus 1. Okay, and third row will be 1 plus minus 1, 1 plus 1, minus 1 plus 1. So this will be equal to a square, b square, c square, 1 minus 1, 1 minus 1, 1, 1, that is the first row is going to remain as it is. 1 plus minus 1 is 0, minus 1 plus 1 is equal to 0, 1 plus 1 is equal to 2, 1 plus minus 1 is equal to 0, 1 plus 1 is equal to 2, and minus 1 plus 1 is equal to 0, right? Now I'm going to expand the determinant along the first column. So expanding the determinant along the first column, I'm going to get this as equal to a square, b square, c square into minus 1 into the determinant obtained after removing the first row and first column, that is minus 1 into 0, 2, 2, 0. Again, minus 0 times the determinant obtained by removing the row and column in which the 0 is lying, but 0 into any number is 0, so I'm going to write straight away 0, and similarly the third term will also be equal to 0. On solving this, I'm going to get 0 minus 4, so this will be equal to minus 4. So the value of this expression would be equal to a square b square c square minus 1 times minus 1 into minus 4, that will be equal to 4 times a square b square c square, which is equal to RHS, and hence the given question is proved.